we're looking at dilations and similar figures. So as we get started, let's talk about the definition of a dilation. Well, a dilation is just a transformation that changes the size of a polygon without changing its shape. I'm going to add one word here, and we'll talk a little bit later about why I'm adding the word usually. But for now, I'm just going to add that in. There's a couple of things that determine what a dilation does. Those are the center of dilation and the scale factor. And dilations are represented using the coordinate notation shown here, where K is the scale factor and the center of dilation is the origin. Today we're going to be focusing primarily on dilations where the origin is the center of dilation. So some properties of dilations. Well, they preserve angle measure, betweenness, collinearity, and orientation. What does that mean? Well, for one thing, in a dilation, such as the one shown right here, angle measure is preserved. So angle A is going to be congruent to angle A prime. Angle B is congruent to angle B prime, and angle C is congruent to angle C prime. All of the other angles in these diagrams are also congruent. I've just only marked these ones. Another thing that's preserved is betweenness. So X is still between A and B, and X prime is between A prime and B prime. Collinearity is also preserved, which means at the beginning, A, X, and B were all in a line. Well, now A prime, X prime, and B prime are all in a line together. Collinearity is preserved. Now, orientation refers to the order of the letters. As long as the letter order is preserved, then orientation is preserved. Another key thing to know about dilations is that the corresponding sides of the preimage and the image will be proportional. And as we said, the corresponding angles will be congruent. Here's a statement describing how the sides are proportional, the corresponding sides. And these statements say that the corresponding angles are also congruent. So now we know a little bit about dilations. Let's investigate whether this example represents a dilation. I can see that angle measure, collinearity, and betweenness are preserved. What about orientation? Well, yes, because my letter ordering is preserved. A corresponds to A prime, B corresponds to B prime, C corresponds to C prime, and D corresponds to D prime. So I would have, if I started at A, I would go A, B, C, D. Or on my image, I could go A prime, B prime, C prime, D prime. Of course, I could have gone the reverse order as well, or started at a different vertex. But however I did it, my letter ordering would have been preserved. Let's look at our corresponding sides. It's easy to find the lengths of BC, CD, B prime, C prime, and C prime, D prime, and also of AD and A prime, D prime. For my remaining side, I really need to use the Pythagorean theorem. So now that I've used the Pythagorean theorem to find those side lengths, I can write that ratio as the square root of 5 over 2 square root 5. And of course, all of these ratios that I've written are actually equal to 1/2. So all of the characteristics of a dilation hold true for this example. So I would say yes. Now that we know a little bit about dilations, let's talk about how the scale factor affects a dilation. And on this activity, we just are concerned with, is the scale factor greater than 1, less than 1, equal to 1, or is it even proportional? Do we have the same scale factor vertically and horizontally? So for our first example with Pikachu here, we go from small to big. And it appears that our pre-image increased by the same factor both vertically and horizontally. So in order for our pre-image to grow, we need our scale factor to be greater than 1. In this case, I can see that we grew horizontally. That means we stretched wide from left to right. And I can see that we grew vertically. It got taller. Would you say these are similar? Yes. Now we're just looking at a glance here, but yes. To be totally sure, we'd need to measure them. But for this, we're just going to talk generally about the properties of dilation. So that's good enough. So because our horizontal and vertical scale factor were greater than 1, our image grew in both dimensions. And since it grew proportionally, it grew with the same factor, both vertically and horizontally, it resulted in similar figures. So just the opposite's happening with our pit bull here. Here we're going from big to small, and both our horizontal and our vertical scale factors are less than 1. Once again, it appears that we have similar figures. And I'm not sure exactly what the scale factors of dilation are for these dilations, but I'm guessing that the top one might be about 1.5. And if we multiply both x and y by a factor of 1.5, this is how we would write that. And that's going to be a pretty good description of that dilation right there. Now let's look at our dilation where we got smaller. It looks like that little dog is about half as tall as the big dog. So I'm just going to estimate that k equals 1/2 or 0.5. And this is how I would write that dilation. And we do have formal names for getting big and getting small. When a dilation causes your figure to increase in size, that's called an enlargement. And when it gets smaller, that's called a reduction. So Pikachu was enlarged and our pit bull was reduced. Now, these next two examples are not actually dilations. Can you tell why not? Well, the corresponding sides are not going to be proportional to each other because it wasn't dilated by the same factor vertically and horizontally. With the bag of Takis, we definitely went from bigger to smaller, at least when you think about the height. But it looks like the width stayed the same. I'm going to use X to represent whatever that width is. So the width is the same for both, and it looks like the height of the second one is about 1/2 or maybe 1/3 of the height of the original pre-image. I'm going to use 1/2 here. So here our horizontal scale factor is equal to 1, and our vertical scale factor is less than 1. So this is not a dilation. The corresponding sides are not proportional. We could write the rule this way. It's still a transformation, but it does not result in similar figures. It just resulted in a squished bag of Takis. So now let's look at our Skittles. This time our height stayed the same. I'm going to use Y for the height again. And our width increased. I'm going to say that it doubled. So we went from X to 2X. So our horizontal scale factor is greater than 1, and our vertical scale factor is equal to 1. It didn't change at all. The height's exactly the same. So we could write the rule like this, and again, this isn't a dilation because we have different scale factors for each of our coordinates, and it does not result in similar figures. So remember I told you earlier that we would talk about a special case when it doesn't change size. In this case, my pre-image and my image are congruent. That's because I dilated my pre-image by a factor of 1. When k equals 1, the size does not change. It's still a dilation, it's just by a factor of 1, so it doesn't change anything. So what if instead I multiplied both x and y by -1? Here's another case where my size doesn't change. In fact, all of the characteristics of dilations are preserved. The only thing that happened is it kind of flipped upside down and backwards. But angle measure is preserved, betweenness is preserved. See how the k is still in between the s and the I? Collinearity is preserved. Those letters are still in a line, and orientation is still preserved too. They're still in the same order. My corresponding sides are proportional and my corresponding angles are congruent. So this is a dilation. It just didn't change the size. So that's just something to be aware of. Your dilations usually change the size, but not always. Not when you multiply by a factor of 1 or -1.